Hello everyone, welcome to my channel Ankura Education. Most of the students face difficulty in solving problems, but it's as simple as by hearting the theory. First of all, for solving any kind of problem, we should notice the given data first. That means we have to read the question properly and what parameters they have given to us, we should note it down first. Then after that, what they have asked to find, that is the second thing we have to find from the question, and we should select the suitable formula and apply that formula to our problem, and that means we have to adapt that formula according to our situation, and we should substitute the parameters that are given to us in the formula, and we should find out the unknown parameter. That's it. It's as simple as this. Now let us do some problems based on the previous discussions. Consider the given problem. Argon resonance radiation corresponding to an energy of 11.6 electron volts falls upon sodium vapor. If a photon ionizes an excited sodium atom, with what speed is the electron ejected? That we have to find. Given the ionization potential of sodium is 5.12 electron. In order to solve any kind of problem, we should note down the given data first. So, given the energy of argon is 11.6 electron volts, 11.6 electron volts, and the ionization potential is given by 5.12 electron volts. Let us say this ionization potential as V. So, what is the definition of an ionization potential? Ionization potential is the minimum potential required to liberate an electron from its parent. So, the energy possessed by the electron is equal to 11.6 minus 5.12, that is equal to 6.48 electron volts. 1 electron volt energy means there is a 1 volt potential. That means 1 electron volt energy implies 1 volt potential. So, we can write this energy as potential also. So, potential V is equal to 6.48 electron volts, and we know the formula that velocity of an electron is equal to velocity of an electron small v is equal to square root of 2 eV by m, where this E is the charge of electron, m is the mass of electron. If we substitute the standard values of the electron, we get this formula as small v is equal to 5.93 into 10 to the power of 5 under root capital V. This is the ionization potential. So, substitute the potential value in this. So, we get the velocity as small v is equal to 5.93 into 10 to the power of 5 into under root of 6.48. If we simplify this, we get small v is equal to 1.51 into 10 to the power of 6 meters per second. So, in order to excite the yellow line whose wavelength is 5893 angstroms. Let us find what has been given. Given is wavelength, that means lambda is given as 5893 angstroms, and what is to be found actually? With what speed? That means we have to find the speed of the electron traveling in a sodium vapor lamp. So, we know the formula that lambda is equal to 12,400 divided by E2 minus E1. We can write this E2 minus E1 as delta E. So, delta E is equal to 12,400 divided by lambda, and we know lambda as 5893 angstroms. If we substitute that, we get delta E is equal to 12.11 electron volts. This is the energy of electron, that means sodium which is traveling in the sodium vapor lamp. 1 electron volt corresponds to 1 volt potential energy that we have discussed in the previous problem. So, velocity of electron small v is equal to square root of 2 eV by m, that is also equal to 5.93 into 10 to the power of 5 into square root of v. So, If we consider this energy as potential, we get capital V is equal to 2.11 electron volts. So substitute that in small v. So small v is equal to under root of 2.11 into 5.93 into 10 to the power of 5. So small v is equal to 8.16 into 10 to the power of 5 meters per second. On simplifying the above expression, we get this. So the electron is moving with a velocity of 8.16 into 10 to the power of 5 meter per second in sodium vapor lamp in order to excite the yellow line whose wavelength is 5893 angstroms. Now let us go for the next problem. That is, a radio transmitter radiates 1000 watts at a frequency of 10 megahertz. That means F is given as 10 megahertz. What is the energy of each radiated quantum in electron volts? And we have to find how many quanta are emitted per second and also how many quanta are emitted in each period of oscillation of the electromagnetic field. Now let us enter into the solution. Now energy of each radiated quantum capital E is equal to h into small f. Given that F is equal to 10 megahertz and we know that H is equal to 6.626 into 10 to the power of minus 34 joules second. So if we substitute this, we get E is equal to 6.626 into 10 to the power of minus 34 into F is 10 megahertz. Mega means 10 into 10 to the power of 6 hertz anamata. So we get 6.626 into 10 to the power of minus 27 joules per quantum. This is the energy in terms of joules per quantum. Now if we want to convert this into electron volts, we have to divide this by 1.6 into 10 to the power of minus 19. 1.6 into 10 to the power of minus 19. If we simplify this, we get 4.14 into 10 to the power of minus 18 electron volts per quantum. This is the energy in terms of electron volts per quantum. Therefore, energy is equal to 4.14 into 10 to the power of minus 18 electron volts per quantum. That means the energy of each radiated quantum in electron volts is 4.14 into 10 to the power of minus 18. The first task is completed. Now let us go for the B bit. 1 watt is equal to 1 joule per second. This we have discussed already. So 1000 watts means what? 1000 joules per second. This is the total energy. This has been given in the problem. So total energy is equal to 1000 joules per second. So energy possessed by each quantum is given by 6.626 into 10 to the power of minus 27 joules per quantum according to the above problem. So total number of quanta per second, total quanta per second, n is equal to 1000 divided by 6.626 into 10 to the power of minus 27. That is equal to 1.5 into 10 to the power of 29 per second. This is the quanta emitted per second. Therefore, the quanta emitted per second is equal to 1.5 into 10 to the power of 29 per second. One more task is also completed. Coming for the third bit, how many quanta are emitted in each period of oscillation of the electromagnetic field? So, we know that one cycle is equal to 10 to the power of minus 7 seconds. So, and the number of quanta emitted per cycle, that means the number of quanta emitted per cycle is equal to 10 to the power of minus 7 into 1.5 into 10 to the power of 9 per second according to the previous one. So if we multiply this, we get 1.51 into 10 to the power of 22 per cycle. So number of quanta emitted per cycle is given by 1.5 into 10 to the power of 22 per cycle. The previous one is per second and the next one is per cycle. So all the tasks are completed and the problem that has been given to us is successfully done. Next problem is, what is the minimum speed with which an electron must be travelling in order that a collision between it and an excited neon atom may result in ionization of this atom? The ionization potential of neon is 21.5 volts. First, let us do problem number A. So, given that ionization potential of neon is given by 21.5 V. That means capital V is given as 21.5 V. Now, what they are asked to find? What is the minimum speed with which an electron must be travelling? So, speed, that means velocity V is equal to square root of 2 eV by m. That is equal to 5.93 into 10 to the power of 5 into square root of V. Here V is given as 21.5. So, small v is equal to 5.93 into 10 to the power of 5 into under root of 21.5. If we simplify this, we get 2.75 into 10 to the power of 6 meter per second. This is the velocity with which the electron is travelling in the neon atom. So, velocity of electron is given by 2.75 into 10 to the power of 6 meter per second. We have completed problem number A. Now, let us enter into B. What is the minimum frequency that a photon can have and still be able to cause photoionization of a neon atom? That means what they are asking us to find the minimum frequency that a photon can have. So, we know the formula that lambda is equal to 12,400 divided by E. So, here 12,400 divided by delta E. So, E2 minus E1 is nothing but the ionization potential. So, 21.5. If we substitute that, we get 577 angstroms. Why we have taken here the energy as a potential? Because 1 electron volt energy corresponds to 1 volt potential. This also we discussed in the previous problem. So, we have taken delta E as ionization potential. That means delta E is equal to V and substituted that value as 21.5. And if we solve this, we get 577 angstroms. Now, frequency of radiation F is equal to C by lambda. This is a standard formula. We know. So, here we know C, that means velocity of light. We know lambda. Then we have to find F. It is that simple. So, substitute C and lambda. So, F is equal to 3 into 10 to the power of 10 divided by 577 into 10 to the power of minus 8. Why? Because this angstroms, 1 angstrom is equal to 10 to the power of minus 8 centimeters. So, we are converting angstroms into centimeters here. So, we are taking 10 to the power of minus 8 here. So, if we solve this, we get 5.2 into 10 to the power of 15 hertz. Therefore, the minimum frequency that a photon can have and still be able to cause photoionization of a neon atom is given by F is equal to 5.2 into 10 to the power of 15 hertz. Now, let us consider one more problem. A photon of wavelength 1400 angstroms is absorbed by cold mercury vapor and thereby it produces 2 other protons are emitted. That means after absorbing a photon of wavelength, it produces another 2 photons. If one of these is the 1850 angstroms line, what is the wavelength of the second photon? That means here in this problem, it has been given that a photon of wavelength 1400 is absorbed by mercury and by absorbing it, it produces 2 more photons. In that, one photon wavelength is 1850 angstroms. Then we should find the other. So, what has been given? The total wavelength of photon is given by lambda is equal to 1400 angstroms. We know the formula that lambda is equal to 12,400 divided by delta E. So, delta E is equal to 12,400 by lambda, which is 1400. So, if we substitute this, we get delta E is equal to 8.857 electron. So, if we substitute that, we get delta E is equal to 8.857 electron volts. And if we consider lambda 1 is equal to 1850 angstroms, which has been given in the problem, then we should get delta E1. So, delta E1 is equal to what? 12,400 divided by lambda 1, which is nothing but 1850 angstroms. So, if we substitute this and solve this by substituting, we get delta E1 is equal to 6.7 electron volts. So, the energy of photon must be the sum of 2. So, delta E1 plus delta E2. It should be the sum of 2 photons. So, we know that here delta E and delta E1 we have already found. So, we should find now delta E2. Delta E2 is equal to how much? So, delta E2 is equal to delta E minus delta E1. That is equal to 8.857 minus 6.7. So, delta E2 is equal to how much? 2.15 electron volts. Now, it is very simple to find the wavelength of second photon. So, delta E2 is equal to, what is the formula? 12,400 divided by lambda 2. Lambda 2 we don't know, and we know here delta E2, which is 2.15. So, substitute that, we get lambda 2 is equal to 12,400 divided by 2.15. So, therefore, the wavelength of second photon is equal to 5767 angstroms. This is our required parameter. So, thank you for watching my video. If you like my video, please do like, share and subscribe to my video. Thank you. And if you have any doubts and suggestions, please do comment in my comment box. Thank you.